My buttons aren't where I want them to be, but that's all right. Last week, we did E1, where we really did the conceptual understanding of why the heck we would want to do this. We found that regardless of whether you're just looking at a function and saying, I would like to find the area under that curve, I'd like to count how many little squares are filled in, right? Which is at the base what we're doing when we're finding area. Oh, I didn't mark Joe absent. Better do that. That is the same as answering a question in context about a rate, right? And the example that we used was a particle motion question. We knew the velocity of our particle, and we made different estimates to figure out how far that particle moved. That's what we do when we're in this new direction that we're going. The function that we're given is a rate, and when we're solving a context problem, we want to figure out how much change has happened because of that rate. One of the words that we'll see a lot, that gets used a lot, that I don't think is here, is accumulation. So how much change has accumulated. It's kind of a weird word, but it is the standard word we use. If our rate represented snow and we integrated that rate, we would find out how much snow fell or how much snow accumulated. So accumulated is really just that generic word for whatever the thing is that's changing, how much change has happened. So we're going to do this. This unit starts out with a lot of the conceptual stuff. It's really how we did derivatives too, but derivatives were broken up into a couple different units. We really hit it all right in the front end of Unit E. So we looked at these sums without giving them names, these Riemann sums. This is exactly what we were doing conceptually in E1. Now we're going to formalize it a little bit. We have a function on the right. We want to approximate the area under the curve between 2 and 6 and they're just using generically n subintervals by using a left rectangular approximation method. So a couple extra words in here. We can approximate this area under the curve from 2 to 6 by making as many rectangles as we want. That is not the right thing. By making as many rectangles as we want. And the more and more we do, hopefully the better approximation we get. They're asking to use a left rectangular method. That just means that you take your left, every time you're drawing a rectangle, you start on the left, find the function, and make a rectangle. So if I was doing n equals 1, I was only doing one rectangle, I would approximate the area under that curve as 8, right? Let me make sure I had the right set of things there, because that's a 2 by 4 rectangle. So when n equals 1, the area is about 8. Is that a good approximation? Probably not. We know it's definitely bigger than 8. That's kind of where a little bit of that underestimate that you wrote on your card came. We can clearly see that we've made an underestimate here. So let's do a little bit better. Let's do 2 rectangles. A left approximation is going to start on the left. Since I'm trying to draw 2 rectangles, I'm going to break my interval in half, and I'm only going to draw that rectangle over to 4. And then I'll draw a second rectangle, but now at 4, I'm going to go a little bit higher. We'll have to do a little estimation here, but that's fine. This is just an example. But now in blue, my area is 4 plus, should we call that 3.1, 3.2? Call it pi. Jack wants to call it pi. Probably not, but we'll estimate it as pi because we know it's somewhere around 3.1 and 3.2. So since Jack wants to, we'll call that a height of pi approximately, and then a width of 2, so that would be 2 pi. And I'm going to change my a to a approximately equal. But we could do even better, and we can go for 4. But the key is, since they've asked us to do a left approximation, each of our rectangles, and maybe I'll erase these because this is going to get a little bit messy. Each of our rectangles, somebody let salmon, should be 1 unit wide. And in this case, the only one that we're not approximating, the first rectangle is a 2 by 1. So that is exactly 2. Somebody give me an estimation for the height of the second rectangle. 2.4, we'll take it. We're not going to do that. We indulged you once, Jack, but we're not going to indulge you a second time. We did already estimate for that third rectangle as a height of pi, right? For Jack, so we'll still give Jack that one.
Let's go.
And somebody give me an estimate for 5. 4.5, sure. Yep. Yeah. Close enough that I'm just going to say 4.5. Any other estimate would be me making more up than I really knew. Cool. So any one of these approximations are called a Riemann sum. They are the pictures you've been looking at the top of the board all year long and saying, what the heck is that? That's what a Riemann sum is. There are 4 different types. You know, that problem specifically told us to do left. And we'll look at all 4 of them today. To introduce some notation here, we use a definite integral to represent the area under a curve. And the Riemann sums are crucial to this definition. So if I wanted math to symbolize the exact area under the curve, I would draw the integral symbol.
Please excuse the interruption. This is a reminder that we will be having a fire drill in a few minutes and procedures to take attendance on Navigate.
That definite integral should have a number below it and a number above it. Those numbers show what part of the curve we're looking at. We're starting at 2 and we're ending at 6. That is the integral symbol, so it's not an S. Do I have any? So yeah, it does. I mean, I know it's small up here, but this is the symbol we're talking about. Yeah, that thing. That is apparently our new.
So they're actually different now?
It is. Okay, picking up where we left off before the fire drill. So that is the integral symbol. It's tiny up there. You'll get to know and recognize it. Looks like an S, but it's definitely different. You put the 2 limits on the outside because when we're calculating an integral, we are in the end trying to find the area underneath the curve. So we need a start point and a stop point. And then we are going to have a function. So that f of x is taking the place of that parabola that we see. And then, what's that? Oh, does it say that it's g of x? Yeah. Then I will update that to g of x then. Yep, I didn't even think twice about that. I thought maybe it didn't say anything. Cool. And then I always refer to this as the language of integrals versus the language of derivatives. Just like a derivative, and you can think some of the fresh stuff in our head, like the related rates. We have to take a derivative with respect to a variable. We have to integrate with respect to the variable. We have to say that we are trying to find the area between the curve and the x-axis. In unit F, we'll actually do area from the y-axis to the curve as well. There's nothing stopping us. There's nothing that says it has to be the x-axis, but we present that in our integral by writing dx at the end. Okay. So in the language of integrals, that's where the with respect to. That is just telling us that x is the variable we're integrating to. It's telling us to find the area from the curve to that axis. Okay. So in our next example, we are going to do the 4 different types of Riemann sums with a function that we actually have. So we'll be able to get exact values if we need them. And we are just going to make a bunch of different approximations for the area under the curve. I believe in each one. Yep, we're going to go from 2 to 8, and we're going to use 3 subintervals. We'll do a left Riemann sum. We'll do a right Riemann sum. A right Riemann sum means that we'll go to the right-hand side of our rectangle to figure out how high to go. We'll do a midpoint Riemann sum, which will mean split the difference and take the middle of the rectangle, which kind of will make, they all make sense in certain cases. And then the last one we'll do, we won't actually call it a Riemann sum, but it's in the same ballpark. We'll actually do a trapezoidal where we won't actually draw a rectangle. We will draw a shape that kind of matches both points on the curve. So we won't do a rectangle because our left will go to a different height than our right. So we'll see all that. So let's do our left Riemann sum first. 2 to 8, 3 subintervals, far from perfect. 2 to 8 is a width of 6. So that means that if we're doing 3 of them, we're going to go 2 across each time. We end up with that rectangle, this rectangle, and then this rectangle. So according to our left Riemann sum, the integral from 2 to 8 of f of x, because it is f of x this time, dx, checking down to the x-axis, is approximately, I'm definitely not going to say equal, because I think it's a pretty solid overestimate. We've got a really big chunk in that third rectangle that is not actually under the curve, right? But it does look like we have two 6 by 2 rectangles, 12 and 12, and that middle is 8 by 2. Gets me 40? Everybody good with where I got those numbers? Okay, just making sure. Sometimes it's the little things that I quickly go past that it's like, wait, what? We have a 2 by 6 rectangle, an 2 by 6, a 2 by 8, and then another 2 by 6. So we are estimating that area under the curve as 40 using a left Riemann sum. Okay. Let's see what we get if we do a right Riemann sum instead. We're still going from 2 to 8, but now when I go to do that first rectangle, I'm going to go up on the right-hand side and draw my rectangle at that height. I'll do the same thing with the second one. And kind of strange, but that height at 8 is 0. So my third rectangle is a rectangle with 0 area because it has no height. Yeah, so it definitely this doesn't feel like a good estimate because we're leaving a lot on the table. But in the end, we're going to make these smaller and smaller and smaller. So it's not actually going to matter. It turns out that they will all, we'll use a limit to do that, and they will all give the same value the smaller you make those rectangles. So here, this estimate tells us that our integral, our area under our curve, is approximately 16 plus 12. And then plus 0, just we could make both of these estimates better by just doing 6 intervals instead of 3, but then that's a lot more work. So kind of just getting the visual here. Questions on either of those? So now for our midpoint, we're going to say, hey, there's some issues that we see, especially when we're going this wide with our Riemann sums. So let's try the midpoint. So when I go to draw the rectangle with a height, with the sides on 2 and 4, I'm going to pick a height of 3. Oop, I hit my button. And use the midpoint to make that rectangle. And then I'm going to do the same thing here, and I'm going to end up with the same point, it looks like, because this is a parabola. And then we'll do the 7, the midpoint here. I have that so low on the screen. What was our f of x? So we can just make sure. I think those are at the halfway points, but we'll just do a quick mental verification. From the previous page, what was f of x? Okay, yeah, 4x minus 1/2 x. I'm pretty confident that if I put the whole number in there, I'm going to get something that's either a whole number back or a half, right? When I plug 3 in there, I end up with 12 minus 1/2 times 9.
So how did you decide the rectangle?
I went to the midpoint. So I went, yeah. So when I was looking at 2 and 4, I went up to the height at 3. Midpoint, yeah. So I'm using 3. And then that's why I'm plugging in f of 3, just to verify that that's a half, and that is 7.5. So yeah. Thanks to Jack, which does match. 12 minus 4.5. 12 minus 4 is 8. Minus 1 more 0.5. Does give us the 7.5. So yeah, so it looks like we have a 7.5 times 2 rectangle. So the integral from 2 to 8 is approximately 7.5 times 2, which is 15. A copy of that same rectangle is 15. And plugging 7 in that will give you 3.5. So that's going to give us, when I multiply it by its width of 2, 7. That sounds like 37 to me. All right. Okay. So if you want to get super technical, if it's a Riemann sum, it has to be a rectangle. The next one that we're going to do is not a rectangle. So we'll just call it a trapezoidal sum. We'll leave the word Riemann off of it, but nobody is going to take you and throw you in jail because you call it a Riemann sum as well. It's not that big of an offense. So we're going to go 2 to 8, and we're going to make trapezoids. It's a sum, yeah. We're still going to add because it's still the same idea. We're trying to estimate the area under the curve, but instead of using rectangles, why not just draw a line connecting those 2 points?
So wait, that is different from trapezoidal approximation.
No, this is trapezoidal approximation. Yep. Yeah. It's a sum. We're approximating by doing a sum. On this paper, this person wrote sum. On my poster when I made it, I wrote approximation. Yeah, I know. Yeah, and it never occurred to me that I used a different word there. Yep, but it is a sum because we're going to approximate using a sum. But now we need a new formula. Rectangles are base times height. That's a triangle, but this is not a triangle. Now, you could, right, now you are correct that you could split this up and make it a triangle and a rectangle, but we're not going to do that. Not that you couldn't in a pinch. A trapezoid, much like a rectangle, you're going to multiply something to do with the base times the height. But since you have, oh, and I guess I should point this out too. When we're talking about a trapezoid, we usually don't draw them vertically like this. These are your bases, and this is your height. Okay, so normally a trapezoid is written with this is what I think of when I think of trapezoid, right? So the bases are horizontal, but when you do a trapezoidal approximation, you just end up with a trapezoid where the bases are actually up and down. So a little bit of weird numbers there. But all you do is you average up those bases and multiply by the height. Okay, so it's a somewhat complicated sounding formula, but if you understand what it's doing, it's a little bit simpler. So you find the average of the bases times the height. That formula is A equals 1/2 B1 plus B2. But for me, it's easier to remember average the bases. And then you multiply that times the height. A rectangle is base times height. A trapezoid is the average of the bases times the height. So in this case, the averages that we have to do are really easy. I have to average 6 and 8. That's 14 divided by 2. So we've got 7 by 2. Nope, I didn't write f of x. Okay, so we've got, I'll actually write out the multiplications on this one. So the average of the bases is 7 and the width is 2. I believe our next trapezoid is going to have the same dimensions, just mirrored. Yep. 7 times 2. And then our last trapezoid ends up kind of being a special case of a trapezoid, which is a triangle. So a triangle is a trapezoid with one base, if you want to get philosophical about it. So we can use, we're averaging the bases. The bases are 6 and 0, or we could just use the triangle formula, 1/2 of 6 times the height of 2. So that's going to be plus 3 times 2. So it looks like we have 14, 14, and 6. I see 20 and 14. That sounds like 34. I'm going to replace my original equal sign with an approximation. 34. If you had to pick one that was going to be the closest, which would you say? Definitely the trapezoidal. Is it an underestimate or an overestimate? Under. Yeah, clearly under, right? Some of them had a little bit of both. If you look next door to the midpoint sum, that had parts where it was underestimating, that had parts where it was overestimating. Well, we got to see there's conditions, and that's what we're going to look at next. There's a little bit to remember here, and there's a little bit that you can sort of figure out. Okay. It does turn out that when it comes to overestimate and underestimate, depending on which sum it is, you have to look for something different. For left and right, you look at increasing versus decreasing. Okay. So left and right, guaranteed do something if your function is increasing, guaranteed do something if they're decreasing, and you can make a sketch and figure it out if you forget. But you have to know that you've got to think increasing, decreasing with left and right. So take a look. If you have an increasing function, the best way to sketch that out is to draw just a straight diagonal line. Does our left Riemann sum over or underestimate? Under. But then again, our right Riemann sum, is that going to be an over or an underestimate? Overestimate. Is that what I had you guys write on your cards? How about that? Yep. So if it's increasing, left goes under, right goes over, and they always flip like that. But then if your function is decreasing, it's going to be the opposite. So you can see that this is a terrible idea if it's an exercise in memorizing, because you're just going to be like, you're going to have things swirling in your head if you do that. A left Riemann sum overestimates a decreasing function, while a right Riemann sum underestimates it. Okay. And that will work for any increasing function. It doesn't have to be a straight line, but you draw the straight line to help you remember that. Okay? All righty. But now when we look at the other two, the more complicated ones, and I guess that kind of like left, right feels simple, so look at increasing, decreasing. Trapezoid and midpoint do the same thing. I've only got trapezoid here, so just kind of compartmentalizing what you need to know. Left and right go together. Once you've figured out one, you've sort of figured out the other. I don't want to overstate this wrong. We're just going to look at trapezoid. If I'm not mistaken, there's a reason why midpoint's not here, and I'm not remembering it at the moment because this is the first time I'm thinking about it in a year. But let's just look at concave up and concave down, and we'll leave midpoint off. I believe midpoint is the reverse, according to my sheets up there. Midpoint is the reverse of trapezoidal. So concave up, we are drawing our lines in. Actually, you know what I'm going to do? Rather than doing individual ones, I'm going to make life easy, and I'm just going to draw one trapezoid. You actually don't need to draw out all of those trapezoids. If I do a trapezoidal approximation on a concave up function, is it an over or an underestimate? Over. And if I do it on a concave down function, I know I'm kind of exaggerating it there, it's an under. Actually, I want to change those pictures out. That should be a parabola. It would make my drawing a little bit easier. But you can definitely do this even simpler with the parabola. If you are concave up and you do a trapezoidal approximation, you should clearly see that that's an overestimate. And if you do concave down and you do a trapezoidal approximation, you should clearly see that that is an underestimate. And that's why it's concavity. Increasing and decreasing, you could see both. That's why we're not looking at it with increasing and decreasing. But concave up and concave down are what guarantee under and overestimate. All right, my goal here is to finish all of these notes today so that when we take our test tomorrow and then have time to work on this on Friday, if anybody needs more time for their test on Friday, they can do it that way. So let's finish this up. I don't think there's anything super difficult here. This next section, though, super common to be part of an FRQ. There are very few years where they go by where they don't ask you to do a Riemann sum based on a table. So we're just missing the picture when we're doing a Riemann sum when we have a table, but the x values, the distance between those x values tell you how wide your interval is. And the actual values in the table tell you how high your rectangles or your trapezoids should be, okay? So you just kind of have to be able to visualize in the background what's going on here. We have a story problem. I'm not sure if it's super important to answer these questions, but it's good to think about. This function that we have is a rate, because when we're integrating a rate, and it's the rate at which water is being pumped into a tank. The Riemann sums that we find are going to be estimates for how much water got pumped in the tank, how much water accumulated in the tank, right? So just to kind of throw those words out at you, just to kind of shift gears away from what we're doing. So we knew the rate, how much water actually got into that tank. We're going to do, it says 4 subintervals. That should make sense on a table with 5 columns because an interval is between 2 of your numbers. So you need 5 numbers to have 4 intervals. If we were drawing this out on the graph, each of our rectangles or trapezoids would be 3 units wide, right? Because those x values are counting consistently up by 3s. There's nothing to say that they're going to give you a table that's always consistent. A lot of times they'll just say, use the information in the table. Some of your intervals might be 3, but some of your intervals might be 2. And that's okay when you're on one of these table problems. And they'll word it so that it makes sense that, yeah, that's what I'm supposed to do. Okay, so if I'm doing a right Riemann sum, then we are doing the integral from 0 to 12 of r of t dt. And that is approximately. Every interval is going to have a width of 3. So we've got to multiply 3 by something. We're doing a right Riemann sum. So should we go, when we're doing that interval, that first interval from 0 to 3, are we looking at the 7 or are we looking at the 13?
13.
Right Riemann sum. Yeah. So you've got a rectangle that goes on your t-axis from 0 to 3.
I know, I just
Right.
left with, left.
Yeah, you would think, I don't know why these are backwards, that we're doing right first. Maybe just to kind of get us to not fall into like autopilot. Yeah, so that first one's going to be 3 times 13. The next one is going to be 3 times, we're now looking at the interval from 3 to 6. So on the right, it's 18 plus 3 times the next interval. The right value is 23. And then plus 3 times 27. Yep. Yeah, so in the end, it's really just a matter of picking which one you're leaving out. To do a right sum, you leave out the leftmost value. If this is something you have to do in your head and all of those intervals were the same, the way I would do this is I would do 3 times the quantity 13 plus 18 plus 23 plus 27, because that's equivalent to what I have written there. I'd do the 23 plus 27 first, because that's 50. And then I would add the next 2, 68, 78, 81. 243, yeah. Yep, 3 times 81, 3 times 243. If those intervals are different, you kind of have to do the multiplications first. But since those intervals were the same, I was good to go. Okay. Let's do a left Riemann sum with 4 intervals, and then we'll answer our, it probably said increasing, yeah. So we'll go back to that. Our left Riemann sum with 4 intervals. Notice how similar this is going to be to our other one. It's just that when I ask for that first interval, now you're going to be picking the value on the left. So the first thing you're going to write is going to be 3 times 7. And then with each subsequent interval, you're just going to pick the next number. So then it's going to be 3 times the next number, 13, plus 3 times 18, plus 3 times 23. So with the left and right Riemann sum, you're just leaving one of those numbers from the bottom out. With the right Riemann sum, we left the first number out. With the left Riemann sum, we left the last number out. What's that? Oh, you got it already? So yeah, so same idea. It's 3 times 7 plus 13 plus 18 plus 23. So yeah, so it looks like I have 20, 38, 58, 61. And that's going to give me 183. 2 ways to figure this out. Our function is increasing. So we could look back to the other page. But since it's one's a left and one's a right, one's an overestimate, one's an underestimate. Look at those numbers. Which one has to be the overestimate? 243, right? The bigger number has to be the overestimate. But that's just me sort of cheating the problem instead of looking back at what we wrote earlier. It does say up at the top that it's increasing. Yep. And an underestimate. All righty. Cool. Okay. So now let's do our midpoint and our trapezoidal. Let's at least get them written out. Worst case scenario, we hit the bell and you guys have to calculate them on your own. So a midpoint, you'll notice that they're only asking us to use 2 subintervals. With the table, I kind of have to do that because I actually need a midpoint. So the idea here being there's one subinterval, there's another subinterval, and the midpoints are these guys. So this actually is going to be a little bit simpler. We're going to use those, now our intervals are 6 wide. And we're going to use the midpoints, which is the R value at the midpoint. So 6 times 13, and then 23, 6 times 23 as well. Right? Because the midpoint of 0 and 6 is 3, so that's why I use that value. The midpoint of t equals 6 and 12 is 9, so that's why I use that value. 6 times 36, which is 6 cubed, which is 216. Yep. Trapezoidal is the most work. I'm going to fix my equal sign, though, in my work there and make it approximate. Get it right there. So we need to get the average of the bases. It's 20, yep. And the average of that is 10. So 7 plus 13 over 2 times 3. And then the next one will be 13 and 18 over 2 times 3. And then 23 and 18 times 3. I'm going to say no, but you definitely do need to show the 4 additions because sometimes that is part of the scoring guide. I always default to like, what do like the super geniuses do? And I could definitely see people doing those quick base averages in their heads. So, yep. And then 23 plus 27 times 3. Okay. So your job to figure out what that all equals up, but the notes for this section are done.